Good day, and welcome to my whiteboard. I'd like to talk a little bit about what we call bond polarity, and this is going to become important later on when we start talking about things like intermolecular forces or the attractions between molecules, although that will be a little bit farther along. To look at this, we need to go a basic concept. That's called electronegativity. The idea is that some atoms are better able to attract electrons than others. Typically those up on the upper right-hand side of the periodic table, closer to fluorine, are much better at attracting electrons than those that are on the lower left-hand side, closer to that of francium. For the most part, that when you have something so extreme, you're going to get an ionic bond. The electrons are just going to move on all over. But when you're still relatively close, not quite so distant, then you can have an unequal sharing of electrons, what we call a polar bond. And we've got a couple of cases. So over here I have water. Water has an oxygen and two hydrogens, and they're going to be sharing electrons, particularly the two electrons that are being shared there, and those two electrons. Those top two belong purely to the oxygen, at least mostly. Once again, electron interactions can get a little bit convoluted once you start diving in a deep enough rabbit hole, but they're the oxygens for most all purposes. Okay, now, that's not an even sharing though. Oxygen is better able to attract the electrons. So, the hydrogens are going to be a little bit exposed. They're not going to have the full shielding of the electron. We're going to say that they have a partial positive charge. We're going to use a lowercase delta to indicate this. And of course, the oxygen has a surplus electrons. And while it is not a full electron more, it's not like it has actually stolen the electron. It's just sharing the electron such that it has the electron a little bit more often, or a little bit more of the electron, depending on how you want to think of the electron. That's going to give it a negative charge, but it's not a full negative charge. It's not going to be as much as if it had actually taken the electron. So it's going to have a partial negative. Or once again, we're going to use a lowercase Greek delta. Okay, we have these partial charges. And we can actually start looking at the uneven sharing by drawing an arrow. And the way we do this is we draw an arrow pointing to the end that's going to have the negative charge on it, or the partial negative. And we put a plus sign at the plus end of the arrow. And of course, I can do it on the other side. Now, these are vectors. Vectors have magnitude and direction, and they add such that when you look at opposing directions, they will cancel each other out, and in the same direction, they will add to each other. So this means that the water molecule has two polar bonds. This side to side, however, is going to cancel out since they're both pointing in, but they're both going in a somewhat upward direction. So these two vectors will add together. Water, as a molecule, is very polar because it's got two very polar bonds that do add together in a way that makes it, well, polar. So let's take a couple of other examples. This is formaldehyde. Now, formaldehyde does have some polarity going on here, but it's not quite what you would think. The carbon and hydrogen bond happens to be nonpolar. The amount of electronegativity between both the carbon and the hydrogen are relatively close. They share their electrons quite evenly. So these bonds have no meaningful unequal sharing. They're what we call nonpolar. But that one's polar. And missing some lone pairs. So, formaldehyde is a polar molecule. However, less polar than water because it's got somewhat less of an extreme pull, and, well, it only has one polar bond. If I look over here at my ethane, in this case I have carbon-carbon bonds. These atoms are identical. They have no difference in pull, so the carbon-carbon bond itself is nonpolar because, once again, it's like a tug-of-war between you and your clone. It's an even match. The carbon-hydrogen, that's likewise. Electronegativities are quite close between those two, so an even match. This molecule is truly nonpolar, and when we deal with intermolecular forces, that's going to come into play. Now, this is carbon dioxide. He's an interesting, quirky little molecule. 2 bonds, the same one up there. I'm going to have polarity going that way and going that way. But look what's going to happen when I add my vectors together. They're going in opposite directions. They're going to cancel each other out. While my bonds are polar in my carbon dioxide, because of symmetry, the whole molecule is nonpolar. And so it's going to, once again, be nonpolar, and its intermolecular forces are going to share that. With that said, have a wonderful day.